All right, so the first thing we're going to look at is a couple of functions that were not on the chart. That we encountered, a fair bit in this class. The f of x is equal to x cubed. We've seen that one. We've seen x cubed things already when we were doing increasing, decreasing intervals, local maxes and mins. We've seen some things with x cubed. So, just glancing at that particular function, there's the equation. And if I graph that, I'll show you what it looks like. You could graph it with a calculator, get an idea. I'm just going to sketch it because I already know. Yes. Well, I mean, I would graph it to get the idea of the picture. Graphing it on the calculator is a great idea. I'm not doing a fine job drawing it. That's a little better. All right, so it's kind of that shape. If you look at the table for that, x and y, -2, -1, 0, 1, 2, 3, get the same table that's on our chart out of that. If you plug in -2 to x cubed, that'd be -2 times -2 times -2 is -8. -1 would be -1. 0 is 0. 1 is 1. 2 is +8. And 3 would be 27. No, I didn't draw my graph big enough to show that point. But the first 5 points, I actually plotted on my graph to get that picture out of that. Okay, so from there, some of the characteristics of that. What's the domain? It's from -infinity to +infinity. It's all real numbers because there's no red flags on that equation at all anyway. So no big deal there. The range, and this is where the graph can help you. In finding the range, a lot of times graphing it is one of the best things you can do to find the range. It just makes range is a little bit more difficult than domain to find from the equation because you don't have the equation is based out of x, not out of y. So the range for this one goes from -infinity up to +infinity. So it's all real numbers as well. And then in its current form, it's increasing across the whole domain. So it's got an increasing interval from -infinity to +infinity. Okay. And I think I indicated that on some of these by just doing that out to the side. That meant it was increasing across the whole domain. That's what I'm trying to indicate on the chart there. Intercepts. It's got an x-intercept and the same intercept for x and y here, 0, 0, the origin. Nothing really major of that. Doesn't have a decreasing interval. Now, when you start adding other stuff to it, that's when the shape gets that kind of hump shape in the middle where you got a local max and a local min. That's how you can get some different intervals and increase and decrease out of that when you start changing this. So its basic form is really straightforward. But when you start changing that and putting like an x squared with it or a 5x or something like that, added to the x cubed, that's when it starts taking this and kind of reshaping it some. And we'll talk about that some in section 3.5 more what's going on. There are certain rules that have to happen, and we'll just learn those and figure that out. So we get everything in. Absolute max or min, does it have one? No, neither of them. Doesn't have an absolute max, doesn't have an absolute min on this. Okay, make sure we got everything else. Intercepts increasing, yeah. Symmetry, the last thing. Origin, yeah, if we flip it across, so symmetry is on the origin. Okay, so real basic idea there. The cubic function is what that's called. Cubic function. What's the name of that? It's cubic function. And Hannah, I'll get you the filled out version of that. All right. Example B. Let's do the constant function. That's what this is called. It's even more basic than that. It's really easy. F of x is equal to some number. And I'm just going to pick a number. I'm going to pick -3. It doesn't matter what number you pick here. It's just f of x is equal to a constant number. It doesn't have a variable. It doesn't have x in it. Okay. The graph of that, which way? Horizontal straight line, yes. I'd go to -3 and go from there. The table for that is very boring. -3 the whole way down. No matter what x is, y is -3. That's what the function says. Okay. Characteristics domain. It would be from -infinity to +infinity. The range would just be -3. Yeah. And I want to bracket in -3. There's no other numbers that are in the range. It doesn't go up or down any other places. Whatever it's equal to is the range. Whatever number it's equal to is the range. And then, let's see. We'll do intercepts. It's an easy one. It's got a y-intercept at -3, so 0, -3. Is it increasing, decreasing? Constant. It's an entire constant interval, so the whole domain, it's constant. Increasing, decreasing, constant. It's constant across the whole domain. Okay. Absolute max or min? Not really either, because it doesn't, it doesn't have a highest point or a lowest point. All of these points have the same height, the y value, so it's not gonna have an absolute max or min. Symmetry, y-axis. Okay, symmetry over the y-axis, and then that's it. That's all that's going on with the constant function. Really, really simple idea. And then what I had for example C was the reciprocal function, which you actually had that on your chart, so I don't have to do that. You may have a graph, and you have to recognize which one it is. Maybe a graph, and you got to say, okay, is it maybe a multiple choice question? Is it the constant function, the square function, cubic function, that sort of thing? Or I may give you the graph and say, what's the domain of it? That sort of thing. And by recognizing what kind it is, you can tell that. The basic, all of this information is of the basic type of problem it is. And then what's going to happen, especially, they do this in 3-4 because you're going to use parts of this in the piecewise. But then in 3-5, what we're going to do is take these and move them around. And if we know this stuff, when we move them a certain way, we know it changes the domain. If we move it left or right, it changes the domain. If we move it up or down, it changes the range. And ever how much we move it, that's how much it changes either the domain or the range. And then we'll talk about how it stretches or shrinks vertically and horizontally and all that stuff. So knowing all this basic information is going to help us find the information of our transformed or translated function in section 3.5. So this is kind of a preliminary part that's going to build up to helping us in 3.5. So kind of be working toward committing that. You'll pick up a lot of it as we go when we're working through some of this stuff, and then go from there. So let's talk about piecewise defined functions. This is where we'll hang our hat. This is the part that piecewise defined Piecewise defined functions are functions that are made up of multiple pieces. Piecewise. Okay. So when you're dealing with a piecewise defined function, you're going to have parts, and I'll call them part A, and then they're going to give you they're going to put a comma, and they're going to give you the domain of part A. They're going to give you a certain domain. It's not necessarily the whole domain for that particular function, but it's saying, okay, it looks like this when x does this. So they may say when x is less than 5 for the first part. So you know that the graph when x is less than 5 looks like part A. And then you get a part B. And they'll give you a domain for it. And then a part C. And it could be a part D and so on. You could go on for, ever how many. 3 is about the biggest we get, parts out of that. It gets a little crazy if you get more than that. As far as, it's just the same thing over and over. It's just more of it, okay? So what we're going to look at is we'll start with a pretty simple one. And we're gonna look at the graph of that and then go into looking at maybe the domain of the whole thing and the range of the whole thing. So let's look at that. Example C, we'll call this, we'll just call this one f of x. And here are our parts. 3x plus 2, x is less than negative 2. 6, negative 2 less than or equal to x, less than or equal to 4. And then negative 2x for x is greater than 4. Okay. Some of you may have seen this in Algebra 2. Some of you may not have. Okay. Depending on if you took Algebra 2 last semester, I know you saw it from me or Coach Mack. I know you saw that. If you took Algebra 2 the year before that, I'm not sure you did, and it's okay if you didn't. I'm going to teach it like you never saw it anyway. Okay. So the easiest thing for me to tell you to do here is do it one piece at a time. Don't try to do the whole thing at once. Do it one part at a time. So I'm going to work with part A first and find the stuff I need for that. Okay. So when you're trying to graph a piecewise defined function, you can't just go, oh, this is 3x plus 2. That's a linear equation. I'm going to go to 2, put a point, then count my slope. It doesn't work that way. Okay. It works kind of that way, but we've got to look at some rules. The rules we have to look at are here, the domain. That's the thing that rules everything. That tells you where it's happening at. So it's telling me that the graph looks like 3x plus 2, but only where x is less than negative 2. Okay? So what I've got to find is what I call important points. The important point for part A is where this x value exists at negative 2. So I'm going to find that important point because that's a big spot for this graph. Okay? So the important point for this part would be at negative 2. And then how do I find the y value for negative 2 for part A? Plug it in, right? So negative 2 times 3 is negative 6 plus 2 would be negative 4, right? Now, I'm going to go to my graph. We're going to come back up here and do part B and C. But I'm going to go to my graph, and I'm going to draw that point. Now, I've got to keep some things in mind. So get your coordinate plane drawn. We do want to be kind of precise on this. I'm going to go to negative 2, negative 4. Now, here's the thing I've got to look at. On that domain, is negative 2 included? No. So the point, negative 2, negative 4, cannot be included. So when I go to graph that point, I don't put a dot, I put an open circle at that point. So there's negative 2, negative 4, and I'm putting an open circle there. Because that point's not included, because this didn't have an equal to mark. That's important. That makes some sense there. If we're not including something, it's open circles. Remember when you did inequalities on a number line, you used open circles and closed circles, that sort of thing. So on a coordinate plane, you can use that same idea. Okay. Now, what we need to do is think, okay, This is happening, 3x plus 2 is happening for x's that are less than negative 2. Which direction is that? Back this way, right? So I can't count my slope up 3 over 1, but I could count it which way? Down 3, left 1. That's still a positive 3 slope, right? And it gets the picture of that graph. I would go down 3 and left 1 because that's negative 3 in the rise direction and negative 1 in the run direction. And rise negative 3 over negative 1 is still positive 3. It's the same slope.
Wouldn't negative 3 be going in the other direction?
No, slope is rise over run.
Wouldn't negative 3 go down?
Yeah, that's what I did. Down 3 over 1. That's how I got here. No. Not if I'm doing a positive slope. I can't go to the right. If I'm doing a positive slope and moving, what does a positive slope look like? It goes up and to the right, right? Look at the number in front of x, slope-intercept form. Positive 3. So I know it's a positive slope. Normally I would go up 3 over 1. But to get the same positive slope, I know I've got to go this way. I can't go to the right because the domain restricted that. So I'm going to go down 3 and left 1. Get a point there. I could go down 3 and left 1 again and get another point. And then my line only goes in that direction. So we've got this direction. That's all these x values that are represented by this red line as it continues are less than negative 2. So that's graphing that part for the domain x is less than negative 2. 3x plus 2 for x is less than negative 2. If you had drawn it normally, you would ran into negative or positive 2 as a y-intercept, but the x values were restricted, so we had to cut it off. Okay. Now we've got part A done. Let's go to part B.
Part has that open circle. When you went down 3 over 1, did you have a closed circle?
Yes, because all of those x values are included because they're less than negative 2. All right, so part B is f of x equals 6. So what function is that? A constant. So it's going to look like what? Horizontal straight line. Okay, we know that idea should be in our head. Okay, so what are the important points for this domain? Negative 2 is the x value, and 4 is the other x value. What's the ordered pair that goes with negative 2? Negative 2, 6. Because the y value is always 6, right? And then 4, 6. Now, question is, are those included? They have an equal to mark, so yes, they are. So should both of those be filled in dots or open? Filled in. Filled in dots, not open circles. So we're going to go to negative 2, 6. 1, 2, 3, 4, 5, 6. Filled in dot. And then I'm going to go to 4, 6. Filled in dot. We already know that the line in between them does what? Just flat, straight, constant function. And now we finished part B. Let's look at part C. It happens for x's that are greater than 4. Okay. So where would we find the important point for that? At 4, negative 8. By plugging in 4 to this, negative 2 times 4 is negative 8. Okay. Is that point included? Why not? No equal to. It's just greater than. Okay. So I'm going to go to 4, negative 8. 4, 6, 7, 8. Open circle. Make sure I counted correctly. And then it says it looks like negative 2x, which is what kind of picture? It's going to be a straight line, right? With a slope of -2. So how do I count that? Which direction am I going? To the left or to the right? X's are greater than 4. So I'm going to the X's that are bigger than 4. So I'm going this direction. So when I count my slope over here, I can go the normal way. I can go down 2 over 1 because it's a -2 slope. Normal method of graphing that. This takes practice. This is not something you'll master in one example, I promise you. Okay? Now, let's look at this in terms of the entire picture. Now that we've done each part individually, let's look at it in terms of the entire picture. What would the domain of f of x be? And we can get that from the function. Are there any numbers that are left out? There are? Well, -2 is left out up here, but it's not left out here. And 4 is picked up right there, but it's left out here. So there aren't any numbers that aren't picked up by one piece of this. So our domain would be all real numbers. So -infinity, positive infinity. It's not. Here it doesn't have an equal to mark, but on the next piece it does have an equal to mark, so it's not left out. It picks it up. There are no x values that are left out in the whole picture. Individual parts they may be, but on this one there's none in the whole picture that are left out. Okay. The range. Now this is where the graph really is helpful for the range. Look at what y values might be left out. All right, so start right here. That's a -4, right? It's an empty circle, so it's left out. And then, is there any graph in this area? No. So from -4 up here to 6, is 6 left out? No, it's included. So when we look at our range, both of the bottom pieces there, both of those pieces go to -infinity, right? So our range would go from -infinity up to the, this is an empty circle, but that same y value is picked up over here. So it's not really left out of the whole picture. And as I go up, this is the first y value that's completely left out, -4. So -infinity up to -4, parentheses, union, -4 to 6 with a bracket, good. And then does it union anymore? Are there any more y values above 6? No. So we're going to stop because there's no y values above 6. It doesn't go up. Okay. So our range is that. So being able to find domain and range of those can, the graph is going to be helpful in that, I promise you. No question. All right. Now let's look about intercepts. Some of this special characteristics of regular small functions we can find with piecewise as well. So let's look at intercepts. Zero 6. We can see that on the graph. We can see it's at 0, 6. Are there any others? No. Now, one important thing to look at here is, maybe you don't want to graph it every time. Think about 0. Which piece did 0, 6 come from? Which part, A, B, or C? B. Because where's x0 that fits in here? Well, 0 doesn't work. 0 is not less than -2. But 0 is between -2 and 4. So this is where the y-intercept would come from, where x is 0 fits. Okay? And then, We don't see any x-intercepts on our graph, but if we were to look at that, honestly, you could set every piece equal to 0 and solve it and see if that x value fit in the inequality. If it does, then you might have an x-intercept there. If it doesn't, then you don't have an x-intercept there. We'll look at some as we go through examples here that might have an x-intercept. This one doesn't. Okay. Obviously, no symmetry in that one at all. Absolute max or min? No absolute max or min. Now, there's this other thing that we want to talk about here called continuity. What word does that make you think of? Continuity. C-O-N-T-I-N-U-I-T. Continuous. Constant. Continuous means I could draw this without picking up my pencil. I could make one continuous motion and draw it. Can I make one continuous motion and draw this? No. So this is not continuous. So we would call it a discontinuous graph. Discontinuous. Okay. So based on that, and I'll get you again the filled out version of that. Those were my blueprint copy of them. So continuity, can you draw it without picking up your pencil? If you can, it's continuous. If you can't, it's discontinuous. That's the way you want to think about that. All right? Can you draw it without picking up your pencil? If you can, it's continuous. If you can't, it's discontinuous. All right? All right. Do enough. Let's call this one g of x. And the first piece on this one, it looks like x squared. For x's that are less than positive 2, and then negative 3x plus 5 for x's that are greater than or equal to 2. Okay. All right. So we've got 2 different pieces, only 2 on this one. That's good. That means we got less to do, right? What is the important point for part A? 2, 4, right? Plug in 2. 2 squared is 4. Okay. Is that point included? No. Okay. So when I go to draw my graph here, at 2, 4, I'm going to put an open circle. What does that look like, and what direction does it go? It's a parabola. Very good. Absolutely. It's a square function. It's the parabola shape. What part of the parabola shape? Am I moving my x's to the left or to the right? X is less than 2, so I'm moving to the left, right? Okay, so I need the parabola shape starting here and going this way. Okay, what are my ways of getting that? I know I could kind of just sketch it, but I want to get 1 squared is 1, so I put that point 1. That'd be an included point. 0 squared would be 0. Negative 1 squared would be 1. Negative 2 squared would be 4. We could get that shape by picking some x values that fit this, that are less than 2. Anytime you don't know what the graph looks like, pick some x values that fit this and plug them in. And you can get ordered pairs, and you can get an idea what the graph looks like. So here we got the left side of a parabola starting at positive 2 and going this way. Because it keeps going, because it's all the x's that are less than 2. So I could go, negative 3 would go up here to positive 9, and negative 4 would be to positive 16. And all those x's keep going because of that domain. So there's why there's an error. Good question. Okay. Not bad. That part's done. Let's go to part B. What's the important point for part B?
-1.
2, -1. I agree. Is that the point included or not? It is included. So 2, -1. Filled in dot. Then it looks like what? It's like -3x plus 5, which is a line in slope-intercept form. How do I count my slope? In what direction do I go? Down and to the right. I'm going to the right because it says x's that are greater than 2. That would be to the right. Notice the arrow inequality is pointing that way. It's kind of a hint out of it. So I'm going to down 3 over 1. I could do that a couple of times if I wanted to, and I will, just because it makes me draw a better graph.
You just don't do anything with 5.
Say that
You
again.
don't do anything with 5.
No, because the 5 is the y-intercept. But the y-intercept occurs where? When x is what? 0. Does 0 fit in this inequality? No. So that's why we can't use the 5 really doesn't do anything to it. Okay. So we're going to go this way. And we get the graph. And again, an arrow on the end of that because it said all x's that go are bigger than 2 for that domain part. Are there any x values that are left out for the domain, for the whole picture? No, 2 is left out in the first part, but it's picked up in the second part. So domain for this would be all real numbers. What about range? The domain would be all real numbers because we got x values that are less than 2. And it goes over here, and then we skip 2 here, but it's picked up here. And then it keeps going forever that way. So that's why the domain would be all real numbers. Now the range, we got up here's positive infinity coming down. Here's a minimum, local minimum for this part of the graph. And then there's this whole empty space right here. So there's some numbers left out. What's that number? 0. Is it included? Yes. Okay. What's this number? Is it included?
Yes.
All right. So we've got a little interval in there that we've got to take care of. So for our range, we'd go from -infinity up to -1, include it. And then where's the next place we pick up? 0. Include it and go to positive infinity. Okay? Domain? Say it again. All right, so range is always read bottom to top. Okay, so this is telling me -infinity. And we're following that up. Here's the point -1, the y value -1. It's included, so that's the bracket. Then I skip from -1 up to 0. So that's the union, and then I pick up, and 0, 0 is included. It's a point on the blue part of the graph. Okay, so I'm going to start at 0, and then this one goes, this side of this goes all the way up forever. So that's the positive infinity part. Okay, all right. Intercepts. 0, 0 is only one. We can see that. That's coming from which part? Part A or part B? Part A. Because where x is 0, that's what's going on. Y-intercept, x-intercept, that's the same one. It's the origin, so that's a special one. Okay. Symmetry? No. Not symmetric at all. Absolute max or min? No. This tells me it's going up forever. This tells me it's going down forever. So no absolute max, no absolute min on that either.
Didn't you say there's a local minimum?
There is a local, so but not an absolute. So if we're looking at the whole picture, no absolutes on this one. Okay. Uh-huh. Okay. Where it's crossing the axis. Right there's the point where it's crossing the x or y axis. That's where I'm getting those intercepts. I'm taking, like these points here, I'm taking the numbers that are in my domain and plugging them into that piece and working it out. And that's getting me the y value that goes with it. So whatever numbers are in these inequalities over here, you're going to plug into that piece and get the ordered pairs that go with it. Then you just got to decide, are they included or not, and go from there. Okay. Equal to marks on the inequalities. Like this one is not included because it doesn't have an equal to mark. The second one is included because it does have an equal to mark.
What does it mean by that?
Filled in circle, open circle. It means it's included. No, it means you can put it in there. All right, goes. Snafu with the air parrot here. Come on. Hang on a second, kids.